Okay, let's get started. So, we're still working on derivatives. And in the recorded lecture for Monday, we talked about trig derivatives. So now we've built up quite a lot of tools for doing derivatives. We have like the sum, product, quotient rule type of things. And then we also know the power law, and we have the trig derivatives now. So that enables you to take the derivative of quite a lot of different types of functions. One thing that we still don't know how to do is, for example, if you wanted to take the derivative of something like sine squared of x plus 1 or something like that. We don't know how to do this. Oh no, wait, maybe we can do this at the moment. Okay, different example, because we can just use the power or the product rule on sine x. Well, let's say we do sine of like x to the 5th plus 3x plus 1. This at least would be kind of hard to do with our current rules. It's possible that we could break this up using like sine of sum and things like that, but we're going to learn something today that will make this much easier to do. So like how to take the derivative of this. So today we'll see how to take the derivative of this. And the basic idea is to view this function as a composition of two functions. So we'll have like the outside function, which will be sine x, and then there's some inside function, which is this polynomial. So we can view this as, say, like if we have f of x is equal to sine of x, and g of x is equal to x to the 5th plus 3x plus 1, then what I want to do is take the derivative of f composed with g of x. And today we'll learn how to do exactly this. So how to take the derivative of a composition of two functions that you know how to take the derivative of. So let me start by just writing down the theorem, and then we'll do some examples. And this is called the chain rule. This says if g is differentiable at some number x and f is differentiable at g of x. So this is once you plug x into g, that's some other number that you would then go and plug into f. So we want f to be differentiable at g of x. Then let's just call the composition capital F. So capital F of x is equal to f composed with g of x. So if we have this function, then the theorem says that this function, capital F of x, is also differentiable at x, and it says what the derivative is. So then capital F of x is differentiable at x, and the derivative is f prime of x is equal to little f prime of g of x times g prime of x. Okay, so this is what the chain rule says. So typically how you will encounter this is more along the lines of this example where you'll just be given some function and it's up to you to decide how to see that as the composition of two functions. So a lot of times that is the hardest part, is just deciding how to break it up into an inside function and an outside function. But then once you've done that, the derivative is just given by this formula. Are there questions about this? We're gonna do tons of examples, like examples all day. Yeah. That was in the recorded lecture from Monday. Yeah. Yeah. So I was out of town on Monday, so I recorded a lecture about trig derivatives. It's on YouTube and there's a link in Brightspace. Other questions? Okay, so let's do some examples. So let's do this example here. Let's let capital F of x be this function, and we'll take the derivative. Okay, so we have to break this up into an outside function and an inside function, and in this case, it's pretty clear how to do that. So we'll have sine x as our outside function, and then the inside function will be this polynomial. So for the outside, we have sine of x, and for the inside, and let me write this out in full. So I'll call the outside function little f of x, and the inside function will be g of x, just like in the theorem statement. So x to the fifth plus 3x plus 1. Okay, so then to find f prime of x, I need these ingredients. So I'm going to have to know what f prime of x is, and I also need to know what g prime is. So I'll go ahead and write those right here. So let's find f prime of x and g prime of x. Okay, so what is f prime of x? Yeah, so it's just going to be cosine of x. And what about g prime? Yeah, perfect. So we just, like for the power rule, I'll just multiply this by 5 and then leave a 4 in the exponent, plus power rule will kill this x, and so we're just left with 3, and derivative of constant is 0, so we just get 5x to the 4th plus 3. Okay, are there questions about either of those two derivatives? So now I'll just plug in using the formula. So we know that f prime of x is equal to f prime of g of x times g prime of x. So my f prime is cosine x, and then I need to plug gx into that. So I'll have cosine of g of x, which is x to the 5th plus 3x plus 1. And then I'm multiplying that by g prime of x. Okay, and that's it. So that's our derivative of capital F of x. Are there questions? Okay, let's do more examples. I will give you a proof of the chain rule as well, but I thought it would be helpful to just go through some examples so you kind of get how it works, and then we'll do that. Okay, let's do the following example. Let's look at square root of x squared plus 1. So we'll have an outside function and an inside function. So what should the outside function be? Yeah, so we'll just set that equal to f of x equal to square root of x. And then what about the inside function? Oh, sorry. That will be the derivative, yeah. So the inside function will just be x squared plus 1, and then its derivative will be 2x. And what about the derivative of f?
That'd be 1 over
1 over
x.
Yeah, or you're just missing a factor of 2. So like, okay, so how do I remember what is the derivative of square root x? I just think of it as a power law. So you can think of this as x to the 1/2. So then to take the derivative, oops. I just multiply by 1/2 out front, and then I have x to the minus 1/2, which is 1 over 2 square root x. Does this make sense? Okay, so then for f prime, capital F prime of x, so I'll write this as f again. So then f prime of x is f prime g of x times g prime of x. So my f prime of x is 1 over 2 square root something, and then I'm plugging in g for the something, so I get x squared plus 1, and then g prime is 2x. And this simplifies a little bit to just x over square root x squared plus 1. Okay, are there questions? Are we happy with this? I think let's do another example. Just to get a little bit more practice. So here's another example. So let's look at sine squared of x. So this we can do, I think there's like 2 strategies you could do to take the derivative of this. One would be to use the product rule, like just thinking of this as sine x times sine x. And the other one would be to use the chain rule, thinking of the outside function as the squaring and the inside function as sine x. So we'll do it both ways and just see that we get the same thing. So let's do like strategy 1. Let's do product rule first. So I'm thinking of this as sine x times sine x. Okay, so for the product rule, what do we need to do? we'll have like, oh yeah, you wanna say?
Yeah, like first times derivative of something plus second times derivative.
Yeah, exactly, yeah, so you're just adding two terms and taking turns, taking the derivative of each of the two factors. In this case, they're both the same thing. So, so how will this look? Let's do the derivative of the left one first. So we'll have cosine x and then leave the second one alone, plus sine x times derivative of the second one. So this is, let's call this. So then in total, this is just 2 sine x cosine x. Okay, does that make sense for the first way? Other questions? Okay, so strategy 2, we'll do we'll do a chain rule where we're thinking of this as sine x inside of a square. Okay, so when I'm doing the chain rule in my life, and this is probably what will happen like as you get more and more practice with it, I don't actually explicitly write down the outside function and the inside function. I'm sort of like picturing in my head that I'm gonna leave this in place, take the derivative of what's on the outside, and then multiply by the derivative of whatever was in here. So for me, that would be, so we're doing power rule, so I'll just take the 2 and put it out front. And then on the side, multiply by the derivative of whatever's in here. So how might this look? So I'll have 2 times leaving the inside part alone times derivative of the inside part, which is cosine. Does that make sense? I think this is like, with practice, you'll just become more fluent with it, and you'll be able to do it without writing down every single step. I will say though, like as far as test taking strategies, like being really careful and writing down every single step might help, because then you can just know along the way that you didn't like do any errors. You know, if you do it in your head, it's hard to tell like if there was an error or not, but if you write down every single thing, then you know that you've done each part right. So, okay, are there questions about this example? Yeah.
Would we need to simplify that to sine 2x, or would that be fine for like that? Like in the exam?
Yeah, just leave it like, yeah, 2 sine x. Yeah.
Like the blind bracket.
Yeah, do you have a question?
So like strategy 1, why did you choose the
So like, okay, looking at strategy 1, I had cosine x times sine x plus this new thing again, right? So that I just have 2 of those things.
for the 2 like
Yeah, so this is like 2 times this quantity, sine x cosine x. Okay, yeah. Are there other questions? Okay, so let's take a break from examples and do the proof. and then we can go back to examples if there's more time at the end. So let's take a look at the proof of the chain rule. So the proof at the full level of generality is a little bit, it's kind of difficult. It's maybe more difficult than you would expect. So we're just gonna prove a special case. And we'll think about whether or not our special case actually applies to the examples that we're worried about. So here's the case that we're gonna prove. So I'm gonna assume F and G are differentiable. And then I'm also going to assume that, okay, so let's say we're taking the derivative at some value x equals a. So what I'm going to assume, I'm going to make an assumption on the function g. And I'm going to assume that g of x is not equal to g of a when x and a are close together. Okay, so is this a reasonable hypothesis?
It is not equal to.
Oh yeah, sorry, is not equal to. So what are some examples of functions that would fail that hypothesis? Yeah. Yeah, so constant functions fail. So what functions? What else fails that hypothesis? One that I came up with was like infinitely wiggly functions. So like our example, you know, sine of 1 over x, because no matter how far I zoom in on that, so like thinking of a is 0. Okay, let's go back, let's do this example again. So this came up when we were talking about continuous functions. So x sine 1 over x at 0. So if I zoom in, no matter how far I zoom in, there's always going to be some value of x where I plug this in and sine of that thing is equal to 0. And that equals the value of the function. So we're defining this to be right, we have to, when we're defining the function, it's undefined, just as written, it's undefined at 0, so we'll just say that it, is 0 at x equals 0. So this function will fail the hypothesis because there will always be places where that function is equal to 0. Let me just draw a little picture of it. So as I get closer and closer to the origin, it's getting infinitely wiggly. So, you know, no matter how far I zoom in on this, there's still values of the function that are equal to 0. What other functions fail the hypothesis? It's kind of hard to come up with examples, right? Like, you can also, you know, define like piecewise erratic functions that would be like hooked up in a special way to fail this hypothesis. But for the most part, like nice functions, when you zoom in on them, right? So like, let's say I just have some parabola or something, and I'm curious about what's going on at this particular X value. You know, on the whole, there might be another X value that has the same Y value, but it is possible to zoom in so that all of the values of the function nearby that point are not equal to the value of the function at that point. Does that make sense? So like, okay, so anyways, this is my hypothesis, and hopefully we're happy with that hypothesis that like this will prove the theorem for most of the functions that we would encounter in our daily lives. Other questions? Okay, so here's how the proof goes with that hypothesis, and you'll see why it was important. So just by definition, so here's the proof. By the definition of the derivative of f composed with g. So I'll just write down the limit, and I'm gonna do the version involving x and a, not the version involving h. So we have the limit as x approaches a of my function, so f composed with g of x minus f composed with g of a divided by x minus a. So this is the derivative of f composed with g. And I'm just going to start simplifying this. So I have the limit as x approaches a of f of g of x minus f of g of a divided by x minus a. Okay, so the goal, of course, is to prove the chain rule. So somewhere it would be nice if in this expression I could see the definition of the derivative of g, right? Because in the end, we're hoping that this is like something like the derivative of f at g times the derivative of g, right? So I'm going to try and massage this expression so that it starts to look like that. And in order to do that, I'm going to multiply by 1, but I'm going to make a clever choice of 1. So my 1 is going to be g of x minus g of a divided by g of x minus g of a. So this is multiplying by I'll put it in quotes 1. Okay, so are we allowed to do this? right? So since we assumed that g of x was not equal to g of a, whenever x was not equal to a, this function is 1 everywhere it's defined. It's undefined at x equals a, but by the switcheroo, we can stick that inside of a limit and it will give the same value. Okay, so now I'll start to rearrange things a little bit and we'll see f prime at g of a pop out, and we'll also see g prime at a pop out. So I'm just gonna switch the two denominators. So I get the limit as x approaches a of f of g of x minus f of g of a divided by g of x minus g of a times g of x minus g of a divided by x minus a. Okay, maybe this is starting to look good, right? So at least this expression, the limit as x approaches a of this is the derivative of g. Right, so that's good. This is still looking a little bit weird, but we can mess with it a little bit more. So I'm gonna use the for limits, we had like the limit laws that told you sort of like how the algebra of limits worked. And we can break this up into the product of two limits. So right now I'm taking the limit of this whole expression, but I can break it up into two separate limits. So I'll just put parentheses to emphasize this point. So I'm going to break this into two separate limits. And then the right-hand limit is the limit as x approaches a of g of x minus g of a divided by x minus a. Okay, so the right-hand one we recognize to be g prime of a. What about the left-hand one? So we had a law, a limit law for the composition of limits, right? And it said, if I'm taking the limit of a composition of functions, then this is really the same as taking the limit of the outside function as x approaches the value of the inside function evaluated at a. Does that sound right? So my claim is like, I'll just write it first and then we can justify it. So this is going to be the limit as x approaches g of a of f of x minus f of g of a divided by x minus g of a. Maybe I'll put some parentheses here just to make it clear that we are multiplying these two things. So okay, so this is what we get. So the justification for this step is by limit composition law. Okay, are there questions about that? Or is it okay? Okay, so then what is this expression? My hint is that it's the derivative of something at something. Yeah. Yeah, so this is the derivative of f at the value g of a, right? So if I just ignore what's in the argument of f, it's like I'm taking the limit as x approaches something of f of x minus f of something divided by x minus something. So what this is the derivative of f at something, which is g of a. So this is f prime of g of a times g prime of a. And that is the chain rule, so that finishes the proof. Are there questions? Yeah. No, but I think this proof, so like, in summary, not all that much happened. We multiplied by a clever choice of one, but then other than that, it was like just straight up algebraic manipulations, right? So it's not really, it's not so bad. Are there other questions? Okay, let's do more examples then. Let's see. Is there, okay, let's do one that combines multiple techniques. So let's do this. Let's do let's take f of x to be 2x minus 1 to the 5th times x cubed minus x plus 1 to the 4th. Okay, so this is fairly complicated looking. How can we start to break up this function into things we know how to do to break it up? Yeah. Yeah, so there's definitely like composition happening, right? Because you have like this inside of a power, and same thing here, this inside of a power. So we will have to use chain rule and power rule. What other rule will be helpful? Yeah. Yeah, we're gonna need the product rule because we have a product of two of these things, right? So, okay, so we're gonna have to, so let's see, we have a product of two things, which are each a polynomial inside of a power. So out of product rule, chain rule, and power rule, which one do we need first? Yeah. Why power rule? Yeah, I think we need the product rule first, right? Because the the product rule will break it up into things that just have less going on, right? Where we'll only have to take the derivative of one of these two things at a time. Yeah.
I don't really understand though, because isn't like the power law in this situation just the chain rule? It's like, is it not like two separate?
I mean,
Like, where did the five and come on front, and then you have to take the derivative?
yeah, so, okay, yeah, so like, let's pretend for the moment that this stuff isn't here. So yeah, if you wanted to take the derivative of this, then you would take the 5 down in front and leave behind a 4, leave this in here, and then take the derivative of that and multiply it on the side. Yeah, but we have like this thing times something else. So we'll do the product rule first. Let's do f prime of x. Okay, so let's first do product rule. Okay, so I'm gonna have the derivative of the left one times the right one plus the left one times the derivative of the right one. So I'll write that as, I'll use the like d dx notation to say what I still need to take the derivative of. So we'll have derivative of the left thing times the right thing. Oops. Plus the left thing times the derivative of the right thing. Okay, are there questions about that stuff? Hopefully I didn't add in any typos. Okay. Okay, so now this is, our situation's got a little bit better, right? We're just taking the derivative of this, which we can use chain rule to do, right? The same thing here, we can use chain rule here. So what is this derivative, the pink one? Yeah.
5 minus 1 to the 4 minus 2.
Yes, great. So here we get 5 times 2x minus 1 to the 4th. So that's our, this is like power rule plus chain rule, right? So times 2 out to the side. Yeah.
I guess I'm wondering why. I guess I'm like the last person. 5. Well, it's really like say like that 5. Why that else? That's correct. Like where like the I guess the necessity of adding the extra back to the side thing.
Yeah.
Why is it just like out?
So one answer that's maybe unsatisfying is just like, because that's what the chain rule says you have to do. On an intuitive level, like if you think about it, so if this was just x in here, like what is the rate of change of this function at a certain value? You know we take the derivative and we find that it's like 5x to the 4th or whatever. But if I instead am putting in 2x, now the rate of change it'll be twice as much because my inputs are changing at twice the rate.
Got it.
Does that make sense? So that's like kind of, I think for me, that's like the why of like, why do we get this extra factor of 2? It's because the, like, as like interpreting it as like a rate of change, the inputs here, we're changing it twice the rate, so that's gonna make the output also change at twice the rate.
So then is it fair to say that the power rule is not something you can apply to just like any old thing inside? X only applies to the very specific.
Yeah, power rule is like
Just X.
X to the whatever, yeah.
But it's only like X or whatever. It can't be like if it's yeah, like some like polynomial in place of X.
Yeah,
You can't just power rule that. You have to do some additional painful
Yeah.
stuff.
yeah, exactly. Are there other questions? Okay, let's continue the calculation. So this was the pink derivative. And then we have this other stuff on the outside, x cubed minus x plus 1 to the 4th, that we don't need to do anything to, plus 2x minus 1 to the 5th. And then we have to take the derivative of this thing. So what is the derivative of that? This will again be like power rule plus chain rule. Yep, that sounds good. So we have 4 times x cubed minus x plus 1 cubed. So that's my power rule, right? I took the 4 down in front and then left behind a 3, and the stuff on the inside stays the same. And then by the chain rule, I have to then multiply by the derivative of the inside stuff, which is 3x squared minus 1. Yeah, and then I didn't simplify it any further than that. It's possible that it simplifies, but I think that like leaving it like this is fine. Are there questions? I had one other example, but we're out of time, so I'll just write it down for you, and if you want, you can do it on your own. This was just sine of cosine of tangent of x. So to do this one, you would have to do the chain rule twice, right? Because like on the first application, you have like derivative of this with all this inside times the derivative of this stuff, which then you have to do the chain rule again to take the derivative of that. Yeah. Oh, yes, that is a good question. But we're out of time, so I'll stop there, but we can stay and do an example with quotient rule. So if anyone wants to do an example with quotient rule, then just stay and we'll do it.